Okay. So I am really excited to have Chris with us. He actually corroborates one of my theories that people that grow up in other countries can think better about other people than people who grow up just in this country. So he's an architect who has figured out so many interesting things to use mushrooms and mushroom mycelium and melanin and all different kinds of substances to build structures and houses for people out of what's theoretically considered waste, and also to repurpose older housing in Cleveland, in the city he lives in, and then take a lot of that material and biocycle it back into the building process. And there's just a lot of brilliant things that Chris has figured out to do. He has a whole list of prizes and really cool architects that he's worked with, and also has been an architect in many different parts of the world, like Anchorage, Firenze, Kigali, Lilongwe. You know, I just loved meeting him. I am so glad that we went to see Jeremy, and then Jeremy said, "Oh, you need to talk to my neighbor." So this worked out so well, and I'm super excited to hear what you have to tell us about your collaboration with NASA and the MIT Center for Bits and Atoms and all the other projects that you've got brewing. I know you said you had 3 separate things you were talking about, so I'm really excited. And then I just want to tell people, if they can put their questions in the chat, if you can type your questions in the chat, that'll help us out. So, yes. So thank you so much for everything you're doing, Chris.
And please mute yourselves so that there's no background noise.
Mute yourself if you're not Chris. So thank you, everybody, for joining. Thank you, Chris.
All right. Well, thank you. It's a pleasure to be here. As Cornelia mentioned, we met through a mutual friend, Jeremy Umansky. I don't know, has Jeremy spoke to your group yet? He did. Great. Yeah, he's a great friend, obviously a fun guy. And he's doing really cool stuff with fungi in his restaurant. And it's just happened to be a coincidence that my architectural office is right upstairs from him, and so we hit it off right away, and we've worked together on some projects. And when Sam and Cornelia came through Cleveland, he was sure to mention that we should all meet up one day. But yeah, this is a good opportunity here to present some of the work that I'm doing as an architect. I'm looking for my slides, and I'm just going to start all over again, and I'll share the whole screen. How about that? Okay, so yeah. Start off by saying I am an architect. I grew up here in Northeast Ohio, but have had the pleasure to work throughout the world. I was a director of an architecture office in Malawi, which is Lilongwe, as Cornelia mentioned. And I was the director for a studio called Mass Design Group in Kigali, Rwanda. And having that experience working in the developing world and using limited resources to create architecture as a necessity was instrumental in my understanding of how the entire planet is actually a limited resource environment. We only realize that when it's thrust upon us by our factors. But as we continue to build with materials that are unsustainable here in the developed world, we just don't realize all of the byproducts or the embodied energy and waste that goes into the creation of materials that we're using. So when I came across mycoterials, as we call them, through seeing some projects that David Benjamin had done for MoMA PS1 in New York, the fact that they could be used in sculptural situations like the artwork that they were doing, and just having moved back to the United States from Africa, I had this, idea that, can't we make materials and food at the same time? And so we started ideating around that, and teamed up with some really brilliant people at MIT to propose this project where we would take the waste bush in Africa. Here you see a picture of our site in Namibia, where in the background there, that's supposed to be grasslands that you see there, but it's encroached by this bush that is causing desertification in this area. So our goal was to see if we could take this encroacher bush that the government of Namibia was looking for sustainable outlets for, and convert that into not only food by way of gourmet mushrooms, but to take the waste from that mushroom farming and create building materials out of that. And so you kind of see that process laid out in a nutshell across the bottom there. You have that thorn bush there. It's called the blackthorn, but people just really call it the encroacher bush because it's so pervasive throughout the landscape and encroaching all of the resources there. It makes it difficult for animal migration. It's hard for cattle farming. And it's just a very unpleasant bush to be around, honestly. So there are lots of folks trying to find outlets for it. Usually that means they're going to burn it because it does make a good fuel. But we think the better option for this bush is to create food and housing. And you see that laid out there where we're growing oyster mushrooms on that as a substrate. It's ground up into a powder, and we grow oyster mushrooms the same way that many of you all grow mushrooms on sawdust. And then the waste material from that, after we take the mushrooms to market, we have the mycelium composites. We'll see some more pictures of that, how that works. And that's put into a press and pressed into these blocks that then can make all kinds of different architectural shapes. And I'll show you just a few of those today. This is the first of 3 projects that I'm going to present, but this is the one that we've gotten the furthest with, and we're in the process of making, the world's first structural mycelium buildings using this material now. So here is another, slide kind of showing exactly how this gets done. We take that encroacher bush, and then we grow our mushrooms in these tall columns that basically make it so it's very easy to harvest our mushrooms. The mushrooms, are basically harvested using a spackle knife, or easily cut off with a bread knife, easy to harvest. And then the mycelium, after those mushrooms are taken to market and used to feed people, it's the waste material from this farming process that goes into making the building materials. So that column of mycelium is then loaded into this press that's basically vertically or horizontally oriented. It will compact this meter-long mycelium composite into something that's about 1/4 of a meter. So it's basically compacted to 1/4 of the volume using, in this case, we have a press that does 200 tons. So it's a lot of pressure that basically forces that into a metal cube, and then we bake that cube, and you get a very strong material out of that. You might be looking at that and seeing the mycelium and think, well, that's kind of foamy, that's a spongy material. I've seen that before, but when you compact it, you actually get something like I'm holding in my hand here, and you won't be able to touch it, but hopefully you can hear this when I knock on that. Can you hear that? No, unfortunately.
Maybe
Well,
knock it on your desk.
yeah.
No, Zoom kills sounds.
Yeah, it's for some reason it's filtering that out, but it sounds exactly like you're knocking on wood. It feels like wood. It has the density of wood. It has the strength of wood, and it basically was wood at one point. Basically, what happened is we took this bush and put it into a pulp, and then the mycelium reconstituted that. What it's doing is exchanging the lignocellulosic material with the chitinous material of the fungal organism. And you're getting the best of both worlds here, because you have that, the strong cellulose from the cell wall of the woody material, and the lignin is becoming broken down, and you're replacing that with the chitinous cell wall of the mycelium. Once that's compacted, all of the other things, all of the waters, all of the things are baked out of that, and you're left with this material that's basically a composite of those two kingdoms together, and it makes a very strong composite. And so we see this working, and the way that we're framing this is that we could grow these mushrooms and have them as value-added goods that can be sold in the developed world, that can help sustain our, firstly, our research and development into these materials, but then secondly, humanitarian causes that we're supporting. So some of these mushroom powders, the mushrooms can be turned into powders, and they can be used to augment the traditional dishes throughout Africa. There are a lot of dishes that are kind of like grits. They're basically just doughy dishes, and they have very little nutrient value to them. But by adding the mushroom powders, you can actually augment that quite a bit and get a material that or a food that has nutrients added to it. And then, of course, there's the housing projects that we're doing. So we actually are finding that if you're profitable in the mushroom sales, you can have these building materials as a free resource for doing humanitarian work. So we could be selling these materials. Someday we probably will, but in the process we're developing now, what we want to do is sell the value-added goods at high-end markets and be able to subsidize the humanitarian work that we're doing. So you see that those objects on the right that can come to the developed world. You might pay a little extra at the store for this impact purchasing product, and some of that money gets sent back to Africa to do the work there that the farmers become enriched from. And so I mentioned that we're building the first structural buildings right now out of these mycelium blocks. If you see the render on the left, this what we're doing there on the right is basically how far we've gotten with this project. We've built a few structures, some arch structures that you may have seen in some of the renderings that we've done, and that we're finding that we're going to go back to basics on this, keep it simple, and we're building basically these orthogonal structures currently that are using these blocks in a more rational and orthogonal way. So this is the image of the single story structure we're doing now. If we click to the next slide, I'll talk about some of the material characteristics of this. So the density is about 0.6 grams per cubic centimeter. Again, that's very similar to wood. So this, water is 1 gram per cubic centimeter. So it's going to float on water. But it feels like a dense material, but it's very lightweight when you compare it to concrete blocks. And that's kind of what we do compare that to, because it has a similar mass as a concrete block at about 10 kilograms. So see, the concrete blocks or CMUs are more dense, but they have basically hollow cores to them, so they become lighter in that regard. But they're pound for pound, this is actually the same weight. The compression strength, we're getting about 6 megapascals in Namibia. And that is pretty much comparable to the strength of concrete blocks in Namibia. So they're closer to about 7 megapascals, but this is much stronger than earth construction or earth block construction, which is commonly done in this area. And the burnt bricks in Namibia are actually much weaker too. So they would be under that 6 megapascal. We've been able to get up to 26 megapascals with our work here in Cleveland, and I'll show you some of that work later. But the rate limiting factor is kind of our presses. So the press that we use in Namibia, we built ourselves, or we had built in country, and it works well for what we need there. But to get to a much stronger material, we would need more powerful and bigger presses to do that. The organic carbon in this is about 43%. And if you multiply that out to the CO2 equivalency, basically every 10 kilogram block that we make stores about 10 or 15 kilograms of carbon dioxide equivalents. So even when we factor in the things that go into making the blocks, which are things like heating and pressing and all of the electricity into processing the materials, we still have a net carbon sequestration in this process. And when we compare that to things like concrete block that are obvious emitters of carbon, we get a huge swing of basically 200% of the weight that we're, every pound for pound that we create, we have about 200% that much carbon dioxide that gets stored in the process. It's a net storage. So these blocks are strong enough to do 1-story structures, and you see several of the designs that we have there. The one on the top right is obviously the one we looked at that is almost complete at this point. We have done arch structures in the past. They work, but they become quite a bit springy because they have this wood-like quality. They have this ductility to them that makes them good in some regards, but it doesn't work very well the same way that masonry units usually do in compression. It's more like a woody material than it is a masonry material. And so you might be thinking, what is 6 megapascals exactly? How can I visualize this? And this is the best way that we found for visualizing the strength of this material, comparing it to a concrete block. Again, the same compressive strength, but when it comes to ductility and ability to absorb an impact, it does much better. So hopefully you were able to see that video. I don't know if my thing is in the way here.
No,
It came out great.
Okay, great.
So Chris, whenever you're ready for questions, we're getting a backlog. So
Okay. I think this is the last slide I have for MycoHab. So this is the first project in a nutshell. I just like to show this video a couple times.
Yes, it's impressive.
It's impactful, right?
It is impactful.
So it's a good way to visualize it. You can see that we did, sustain some damage and the impact there, but nothing like the concrete block. Concrete is famously, brittle and heavy, which is an awful thing to have in earthquake scenarios. But most of the world builds with mostly concrete. They think we're crazy in the United States for using so much wood in our construction, but the wood is a ductile material. It stores carbon. There's a lot of great things about wood. The bad thing is it requires deforestation. So when we talk about using this organic carbon based material that uses a circular resource, we kind of take all of the good things that wood can do, the ductility, the the ability to store carbon and that doesn't go into the atmosphere, and replace that with something that uses a waste resource rather than a raw natural resource like timber. That's where we believe this technology could really make a difference as far as ecology worldwide. If we switch from net carbon emitting technologies to this net carbon storing technology, we could actually leverage architecture as a way to turn back the climate crisis. So I will stop there and invite some questions.
Okay, so I'm just going to start at the bottom. Jeff is asking, what do you use for mortar between those blocks?
Yes, so I mentioned that it's basically like a woody material. I'm going to try and go backwards in my slides here. It's more like a woody material than it is a masonry material. So we actually use woodworking techniques to put this together. We use wood glue and what are called biscuit joints. So if there are any woodworkers here, basically you kind of cut a slot into the material using a saw, and then you put a biscuit, which is actually a piece of wood. It's not a not a food, but the biscuit goes in and kind of connects the two, leveraging that connection to make the wood glue even stronger. So this is basically, once it's glued together, it's almost like a solid piece of wood that's 8 inches thick and 10 feet big, 10 feet tall and 8 inches thick. So a lot of biomass going into there. And so normally when you're putting a lot of mass into a building, that means you're extracting more resources and you're creating embodied energy in this, but it's exactly the opposite when it's a carbon storing material. The more mass we put into it, actually the more carbon we're storing and the more carbon that's not going into the atmosphere. So we actually feel good about having very thick walls. And as an architect, I love it because it feels good to have these thick walls, and it looks good to me. But normally we can't get away with that because we're using resources to do that. In this case,
Right.
those resources are having positive attributes.
It's actually beautiful, the variegation that you're getting on
Mhm.
the outside. That's just
Yeah.
gorgeous, actually, aesthetically.
Yeah,
And so, yeah,
I like it too. A lot of that has to do with the baking of the material, and but yeah, it's a very homogeneous material, but they have different colors to it. Same way, with bricks, that some, when they're closer to the heat source, they get a little darker.
so I think you answered Nancy's question, which is whether you can drill or saw it like wood.
Yeah.
Sounds like
So
the answer is yes.
let me turn
And
my.
and then my brother actually was asking, can you press the blocks into interlocking shapes so that you could just slot things into each other? And I guess you'd have to have the mold. I know you said you built
Uh-huh.
this equipment on site, so have
Yeah,
you?
to change the shape, it requires some complexity to it. And again, if let me jump back to our picture of the press there. So you see this blue machine there. It's a very, very simple machine where, I wish you could see it from the other side, but it's a hydraulic ram that's gonna push all this 1 meter long piece into a quarter of a meter. So a very simple system where it's just gonna squish it.
Right.
And then it goes into these metal molds. If those molds were shaped complexly, it would fit into there, but you have the problem of getting it in consistently and then getting it out consistently. So we found that the simplest way to do that is just to go with a cube. And the simplest way would be a sphere because we're talking about liquids forces, but that's not going to be a very good thing to build with.
Right.
Yeah.
Not. And I actually, going back, I was wondering what the material is around the column that you make where you're
Mhm.
fruiting the mushrooms. Is there something, what's encasing it, or is it, how are you doing that? Normally,
Yeah.
when growers are growing mushrooms, they have plastic sheeting around those things.
That's right. Yeah. So we have done it both ways. So you can see in the picture of the press where we just have the standard unicorn bags that we're growing
Okay.
and that most people use. You can just unload like 5 or 6 of those and put them in there, but the better way to do this is to actually grow it in that one form you see there, and that is a reusable form. It's made out of polycarb or acrylic, depending on what the different models that we've created. But keeping that clean and sanitizing that between uses is very difficult, and that's why most cultivators are going to go with the disposable bags, unfortunately. But we think when we scale this up, we have concepts for having autoclavable models like you see there with that column. But probably more in the form of trays. When we get into the biocycler project, I'll show you what I mean by that. But we want to kind of stamp these into large slabs of material rather than the blocks that you see there. So this is, our first go at this. We wanted to keep everything, simple and just prove, the question was, can we turn this bush into food and housing? And the answer is yes, we
Yes,
can.
that's so great.
So
So
that's,
great.
what we wanted to answer. Now we're going back to folks and looking for different investors and say, here's the very simple, yes, we can. But we want to take this and we add complexity to it and make it, hit all of these positive attributes at high levels.
Right. Well, this was a really good proof of concept,
Mhm.
basically, is what you're saying you did. And so we have a few more questions too. Ed is asking about humidity or mold growth. Is that a concern?
It is a concern. Fortunately, this is, in a very arid environment, so it's a good place to test this. What you don't see in this image here is this is going to all be rendered over with a mud rendering. So, unfortunately, on the interiors, we will keep the blocks exposed. But for the exterior, that's going to be, weather, it's going to have lots of, rain exposure and different weather elements. to deal with. As you see in the render there, we have a rendering, and then there'll be a paint that kind of goes on there as a graphic, but that we're starting to do that now. So we do need to protect it from the elements. It's a lot like building with lumber. Again, you need to kind of protect that from the elements. But you know, if as long as you do that with good, we say a good hat and boots. So you need a good foundation and a good roof. You can get away with exposing some of that to the elements.
And then I think you answered this question on one of the slides, but people are asking about the insulation, thermal insulation value for these bricks. So
Yeah, so what we look for in this part of the world is more thermal mass is the best way to kind of deal with heat, because you have very cool nights and you have very hot days. So what you would want to do is actually store that heat, you know, build up that heat in the material throughout the day and then release that at night. But it does have a good insulation value. It's basically, again, like wood. So if you have, you know, a wall that is solid wood, 8 inches thick, you're going to get an R value of, you know, somewhere near 20 or so. So just, you know, just having that as the raw material. And then if you make that thicker, obviously you can get better insulation. But the raw material itself is a much better insulator than, say, concrete block, again, which we like to compare this to. You can, with some of the lighter, the uncompressed mycelium, you can actually get, you know, as much as an R3 per inch, which is pretty close to fiberglass bat insulation, which is the gold standard or the industry standard for residential insulation.
Right. So we do have some people here that are either developers or working with developers that want to know, like, where could they get a sample of the brick? Or do you have stuff they can show their developer?
So at this point, we're giving samples to investors rather than developers, but yeah, is my camera on or off? I can't tell.
Your camera's off right now.
Okay, let me figure out how to turn that back on. Still off, still
off. So
maybe if I stop my share.
Ask to start video. I just asked you to start your own video.
Okay, great. Oh, here
there you are.
Yeah, so again, you know, here's a sample of material. This is something, you know, that you can't hear, but is very, you know, strong. This is what we made here in Cleveland. The blocks that we're making in Namibia, obviously they would be pretty hard to transport to different places for samples. We're using these in our own projects for the most part at this point. We're not selling them on the market. And again, that's kind of part of our strategy is to kind of, we want to sell the mushrooms, and then we want that to go to the people with the most need, which includes these folks in Namibia that are experiencing homelessness. So we kind of say the materials are free, but you can't have them. You know, at this point, but you know, we are doing some projects through our architectural work where we're actually using this for interior installations for art projects and things like that. So, you know, if there's a project that we're working together on, we could definitely, you know, make bespoke materials for that project. But, you know, all of these materials that we're making in Namibia are going to, you know, the humanitarian causes that we've outlined. So it's a mission-oriented thing.
Right. And I remember when we talked to you, Sam and I talked to you before, that you said you had a couple other parts of the world you were looking at doing the similar project.
That's right. Yeah, and so yeah, as half joking about, you know, giving these materials to investors, we are working with folks that are planning to develop a mycohab in South Africa, a group that's planning on developing a mycohab in Guinea, Uganda, Cambodia, you know, basically, you know, Greece. So, you know, several continents at this point. We were working with a group that was maybe going to do this in Austin too, but their funding fell through. So, you know, anybody that thinks they could use food and housing, or in some cases, we're actually, you know, talking to folks about food and beehives. So it's not housing for people, even it's housing for bee colonies and sustainable farming in that regard too, so that there are different outlets. But basically, what we want to do is try and leverage a waste resource and convert that into as many positive outlets as we can at one time. And me as an architect, I'm always going to push for housing or for architecture as being that outlet. But I'm not particular about the species that we're housing. So bee colony sounds good to me, and if it's a dog house or bird houses, bat houses, whatever, I'm into it.
Well, and there are more questions related to the qualities of the material, like the
Sure.
flammability property.
Yeah.
And I know that from Phil Ross's is the one that does the Michael Leather, and he has
Yeah.
this whole like propane torch ice cream cone thing. But
Yes.
what are
Yes.
your
Yeah, we can do the same demonstrations. It would create quite a bit of smoke in here, but yeah, if I were to put a flame to this, it would burn as long as I had the flame on it. But when I would take that flame away, this would go out. It would extinguish. So that even though this is mostly wood, the mycelium in there actually is self-extinguishing. And when it comes
Nice.
to fire ratings and architecture, it goes by how long it takes something to burn. So if you were in a house that was burning with, this was on fire, you would be inundated with smoke, and that would be a bad thing. But it would not spread to your neighbor's house for a very long time. And so, a material or the walls thicknesses that we have there will be rated at several hours, basically, just because of that, which again is pretty similar to concrete when it comes to that. It will eventually burn away. But if there is another fuel that's basically feeding it, but it is self-extinguishing, and it will have this high fire rating in the sense that it takes a long time to burn from one space to another space. And a lot of folks are looking at that when it comes to cross-laminated timber as well. So this is massive timber walls, so it's made out of wood, so obviously it's going to burn, but it will take several hours to get from one space to another. So it's considered a slow burning or a very fire resistant material, and that's why they're enabling high-rise construction to be built out of that, because of that slow burning characteristic.
And related to that, also someone's asking about sound deadening characteristics of your blocks.
Yeah, it's great sound attenuating material. The compressed blocks like this, they have a good feel bounce to the audio qualities on that. And then again, the materials that are uncompressed, the foamy like materials, they're extremely they have a very high sound noise reduction class. So that basically it'd be similar again to bat insulation, which is kind of the standard for sound dampening in walls.
And I guess this is hard to calculate. Someone was asking your estimated price per square foot. But
Again, it's free, but you can't have it.
okay.
So yeah, like basically the process works that we're making profit off of the mushrooms, and all of this material that comes out of that is a waste product. Of course, it costs us a little bit of money to convert that waste into a usable material, but we're still we're still profitable even after doing all that work. So we just kind of throw that. Let's say we're going to throw that building material into our marketing budget for the mushrooms. So if we give these houses for free, then that becomes something that we can kind of go to the developed world and say, buy, same way that Warby Parker sells glasses and says you're giving glasses to the developing world, or Tom's Shoes did that with the buy one give one. In this case, if you're imagine buying mushroom jerky and giving someone a house from that jerky. I mean, it wouldn't be the whole house, but it would be part of a house, right? And so on our packaging that we're going to sell in the developed world, it will have a QR code, and it will say exactly how much of that material was converted into building material for the developing world.
Cool. Sam is asking, and he's asking because we live in Georgia, like how feasible would this be in a more humid, rainy, wet environment?
Well, do you build with wood there? I mean, I think you do.
Do.
So yeah, the answer would be you need a good architect, and you would basically design this in such a way that the organic material, like wood, is protected from the elements. So we use breathable weather barriers, and we use vapor barriers and different different parts of the wall assembly. And there's calculus to that to make sure that there's no condensation that happens inside the wall cavity. But basically, with standard building technology practices, this could replace any lumber construction. So if you're using 2x4s, you could use this as well.
And then Janelle was asking if you cook them in a kiln or a regular oven, how are you heating them?
So let's see if we can see it. So basically, here's our site in Namibia, and all of the structures, or most of the structures anyway, are made out of shipping containers. So we have our office there in the front, and then you can see these cooling towers on top of each of those shipping containers. One is a laboratory, and the rest of them are grow rooms, or grow rooms and fruiting rooms. And then over here, this larger structure is basically just covering up another shipping container that we turn into an oven. So, all things being equal, we wish we had the, time and resources to make a solar oven. So imagine being able to leverage solar energy to create a kiln out of that. But as time and resources dictated, it does have a burner on it. So we're using fuel to heat that up. But the temperatures in the oven are around 160 C. And so that's similar to, your oven at home when you're cooking. It's less than you would cook a pizza at. So, low temperatures compared to most building material technologies, like concrete, for instance, uses 1400 C. So, about 10, 10 times as much energy.
So, and I also want to make sure we leave enough time for your other projects, because people keep posting more questions, because everything you're saying is so fascinating and just brings up more. But
yeah, some of the stuff will come up in the next projects as well. So I can move on to the biocycler, and we can kind of pause after that for more questions.
Okay, and I think you answered Athena's question about sustaining growth and cash flow. It's basically through your value added products you're selling to the developing world. That's how you're.
That's right. Yeah, that's what our business plan says. In practice, we're still doing everything at an R&D scale, and we're relying on that R&D investment at this point. But the business plan that shows scaling this to a point where we could actually export large amounts of, say, reishi powder, and create reishi teas, and the mud water and Four Sigmatic type products that you often see. Those type of value added goods could go to subsidizing the humanitarian work.
Right. So I was wondering if you're using the encroacher bush itself to fuel your ovens or not, but I think it'd be great if you move on, and I'm gonna kind of earmark where we left off on these other questions.
Sure.
So,
yeah. Okay.
I won't forget other people's questions, but have Chris move on to this next project, and then we'll circle back around.
So this one's a little closer to home for me. We're going to go way out of this world in a little bit, but right now, this is very meaningful for me as a Clevelander. What you might know about Cleveland is, the river caught on fire, right? That was a huge disaster that we had here. But what happened after that was the creation of the Environmental Protection Agency and the Clean Air and Water Act, and a lot of this huge disaster was the impetus for big change. What we have here in Cleveland now is a lot of abandoned homes, crumbling infrastructure that is literally poisoning our children, and mostly through lead dust paint that are in this crumbling infrastructure. So we have 4 times the national average of incidences of lead poisoning here in Cleveland, and it's not because of the water supply, it's because of our housing. Lead dust paint is in the environment, and children are being exposed to that through hand-to-mouth contact of lead dust, on near windowsills, on the floor, getting on toys, and then the children put the toys in their mouth, and they become poisoned by this, and that leads to developmental problems that can plague them for the rest of their life, even when they're older and they're not feeling the effects anymore. For women, a lot of times it's lodged in their bones, and then when they start to have children and breastfeed, they can even pass that poison on generationally. It's a huge problem that we're dealing with. And so what we want to look at is, instead of a mycohab model of creating food and materials from a waste resource, we want to take this waste resource and leverage fungi's bioremediative abilities. Oh, should I start my video? Am I not sharing screen? Are you seeing Biocycler?
Yeah, no, we see that.
Okay. All right. Yeah, I didn't know you wanted to see me too. Geez.
Yeah,
Well, here I
both
am.
are good.
Okay, so yeah, basically this is just a graphic that shows this deteriorating, this blighting of neighborhoods kind of getting converted into something healthier, and the same way that fungi restore the forest through their remediative abilities and their transformative abilities. What we want to do is leverage fungi's ability to remediate communities in this case, and so that's Biocycler, or remediative environmental justice project. And if take a step back, the impetus for this again is environmental justice, and we see that communities of color are disproportionately affected by pollution in our environment. This has to do with decades of racist practices in city planning and banking and industry standards that put communities of color in harm's way. And they're 1.5 times higher exposure to air pollution. Black children generally, at least in this part of the world, have twice the amounts of lead in their blood levels on average. And as I mentioned, Cleveland, where I live, the children here have 4 times the national averages of lead poisoning, and it's not the water supply as it was in Flint. It is the infrastructure that we live in. It's our architecture. So I would like to do something about that, and the concept here is basically to take construction and demolition waste, which is abbreviated as C&D waste, and use the different biobinders similar to what we're doing with mycohab, but instead of creating food and materials, basically we're creating new materials and creating remediation. So you see that graphic along the bottom, basically that imagine this as a meat grinder where you're putting in these old houses and you're popping out these new forms of architecture. So you can not only remediate the materials, but you can remediate entire communities through this process. And so there's a couple ways fungi and biomaterials generally can be useful in this regard. So there are petrochemicals in the built environment. These are things like bitumen and asphalt, and a lot of the treatments that go into wood. They have these polycyclic aromatic hydrocarbons, or different types of hydrocarbons that are in the environment, and you can get an enzymatic breakdown of that. So basically, most of this crowd knows this, but usually explain that the metabolism of fungi is external. So they're secreting these enzymes that goes out into their environment. It breaks down the material around them, and then they can take that broken down material and create their own biomass, or metabolize that into new materials. And so these hydrocarbons that were once woody materials are still have a lot of the same chemistry and are able to be broken down by the enzymes that the fungi excrete for that extracellular digestion. When it comes to things like heavy metals, and I mentioned lead is a seriously dangerous and pervasive toxin that's in our environment, you kind of have to do the opposite. You can't break that down any further. What you have to do is chelate that, or turn that into a larger molecule chain that is then biologically unavailable. And so when people have lead poisoning, what they do is they go through chelation therapy, and that's when different chemicals are attach themselves to the heavy metals in the bloodstream and are able to pass through the urinary system. So this is, basically something we want to replicate outside of the body. We want to do this chelation through the material before it actually becomes a toxin for people. And so between these two mechanisms, basically what we're looking at doing is breaking down the long molecule chains to create safer monomers, and then with the elemental toxins, things like heavy metals, to attach them to larger molecule chains that make them biologically inert. As the mycelium grows over the materials, you can also see a doubling effect of this, where the material that is chelated is then encapsulated by the polymeric coating of the mycelium. So mycelium is chitin rich. It has this cell wall that is very hard to digest without cooking, and so that is actually beneficial in this scenario where you can have a chelated material that is also double encapsulated with a chitinous shell. So this slide you see here kind of could relate to what we're talking about with mycohab as well. But what we want to do is switch from these very small materials, these masonry units, into large slabs of material. So we start with the bricks that you've seen already, and just by growing in larger units and pressing in larger units, we can get to a scenario where we're doing this, what we're calling cross-laminated panels, or cross-laminated mycelium panels. That would be very similar to cross-laminated timber technology, which is kind of taking the architectural world by storm right now. The market share for that is predicted to triple by 2030. And the reason people like this is it's a carbon storing material. It's something that is easy to construct because you can lift it the way you see there. It's very similar in material strength to concrete, but much, much lighter. So it's a lot easier to work with. But the problem with using that is it requires virgin lumber. And again, what we want to do is promote a circular resource that could replace that, well-intentioned new technology of cross-laminated timber before we have the unintended but not unpredictable consequences of more deforestation that comes out of the proliferation of cross-laminated timber. So here are some of the factors again. So again, we're looking at about the same density. So 0.6 grams per cubic centimeter, the mass very high because we're talking about big materials. But we're moving closer to the compression strengths that we're getting here in Cleveland with, using the smaller presses, but, these would be much, much bigger presses, but have a lot of force behind them to create the, 26 megapascals, which again is strong for concrete even. And the reason we can do this, it's hard to imagine a woody material that's stronger than concrete, but the reason this happens is because of the heat pressing of the material. And material engineers are finding they can do this with wood just by pressing that into more compact materials. But what they have to do is heat it to a point that the lignin breaks down before they can press them and make the stronger materials. Well, we know a way to break down lignin, right? Everyone in this room knows the white rot fungi basically can break down that lignin. So by having that breakdown of that material makes the cellulose more easily align, which makes the compacted material much, much stronger and makes it more durable in the long run. And again, carbon sequestration rather than carbon emissions at the end of the day, especially if we're using a circular resource like old homes. Tomorrow's homes are yesterday's homes. Basically, we're talking about literally recycling dangerous material into safe material and storing that carbon, keeping it from landfills. So I will pause there for questions before we get get a little further out.
Great. Oh, there's Michael. Okay, great. So they're actually just, okay, so there's a few new questions. Okay, so somebody was asking about termite resistance.
Yep. So similar to wood, basically, we kind of have to protect it from vermin. One of the things that we do as we're storing materials in Namibia is actually vinegar, so it keeps keeps insects away. It's very acidic in that regard, and so in storage areas, that's one thing we use. But yeah, they have to be protected against vermin the same way they would be protected against the elements.
And then Gail was asking if you use the saw on
Mhm.
these compressed myceliated repurposed wood kind of products, would it release some of the lead again when you sawed it open?
Well, yeah, I mean, all of this is still kind of in research stages with this, but what we're planning on doing is chelating this at an elemental level. So, if the dust was liberated in a certain way, and a child were to eat the dust, that it wouldn't become biologically available. So even if it were ingested, you never want your kids to eat building materials for the most part, but the most dangerous ones are obviously, things that do contain heavy metals. If those heavy metals are already pre-chelated before the ingestion and then, coated in certain ways, then they become something that can just pass through the body. But, not recommended to eat at this point, but theoretically, and again, this is still in research phase, the concept would be that it would become biologically unavailable if ingested.
Okay. And then Barry was asking if you expect any of these to become proprietary technologies, or will they be kind of open source for replication, or what's your plan with the biocycler?
Well, so the work we're doing in Africa is patent pending. We worked with a group at MIT. MIT owns that intellectual property. We're listed as inventors on that, but they have a very impact over income methodology for using their technology, and so they want to get that out into the environment, but they want to be savvy about the business of that too. So I want to make sure that it's protected in a way that it's used properly. We have first crack at this obviously as the inventors, but if we were to team up with someone that could create a bigger impact, someone like a large multinational building material company that wanted to take the technology further, that might be a possibility for, that might be enticing for MIT. I'll just say,
Okay.
yeah. And then, similarly with the biocycling technology, there are proprietary things involved with this, but everything that I've kind of disclosed to you is obviously just conceptual at this point. So that there's that's open, I suppose. There are other researchers that are looking at the bioremediative aspects of fungi in the building world, and but yeah, the chelation technology involves some biochemicals that are could be considered proprietary at some point.
And then Nancy was asking how this material performs under tension.
Mm-hmm.
So
that's one area that the wood is still better. So the tensile forces. So wood is very good in bending, and we're looking at different ways of kind of laminating this, the way that you might have a glue lam or veneer lumber, laminated veneer lumber, that could work also in bending, 3-point bending the same way that wood can. But this being a more isotropic material, it's really great in compression, but doesn't have the bending strength yet that you get in wood. So we're basically designing everything to be in compression at this point.
Okay. Trying to see. Oh, yeah. So Athena, you're asking about how is it possible to get more involved with any of this research that you're doing? Are you taking interns or any of that stuff? You know,
Yeah, I think you've probably disclosed my email address, right? And we're friendly. We like to talk to people, especially fun guys and fun gals like you all. We'd love to talk about what your interests are and how you might plug into this. Again, we're working with folks at MIT, Johns Hopkins, Stanford, a lot of NASA, as we'll see in a second here. So the opportunities to kind of leverage those minds and different creative aspects, there's a lot we could do if you feel like volunteering or somehow getting involved. If there's an opportunity, I'd love to hear from you all.
okay. So I know you have a third part.
Yep.
One question was about if you're pressing the biocycler material into sheets, can you add reinforcement such as rebar?
Yeah, you absolutely could. So we're trying to keep everything as natural as possible in this. We think that the better scenario would be to go again along the lines of a laminated veneer lumber, or plywood sheets are basically just sheets of very thin veneers of wood that have glue in between them. So depending on what kind of glue you use, that could be organic or it could not be. A lot of times that's pretty toxic, the stuff they put into plywood. But what we're looking at is different bio-based glues that could be used in that, and that creates the reinforcing. So just by having those laminated veneers, you get a real good reinforcing system to it. So we have made materials that they use bamboo and different woody material as the reinforcing to it, which is good in bending, but it still doesn't compare to being able to have a wood grain. A natural wood grain is wood is incredible in bending, actually. And that's nature
Right.
designed it that way to bend in the wind, right? So
Right.
that's what we can surpass concrete, but what we want to do is aspire to be wood, because wood is just so great.
So I think you're probably already familiar with this, or we talked about it, but Ecovative has taken mycelium and made particle board, replacing all the urea and formaldehyde glues, just myceliating everything together and then compressing it.
Yeah.
So I don't know is that something you're also exploring with the veneer plywood?
Yes, we are.
creation?
Yeah, so that there's the bio welding ability to actually take sheets of the material that are living, and then they fuse themselves together. That becomes kind of a glue that takes a little bit of time and
Right.
very controlled environment. So developing the processes that you could do that at scale would be pretty challenging, but yeah, there are different ways of actually extracting the chitin from that to create chitosan, and then the chitosan can be used as a glue, and there's lots of natural glue products that could be kind of used in this, that they could make the manufacturing of that quicker and simpler. But you definitely want to keep our eye on the footprint, the environmental footprint of all the different technologies that go into that. And the more you utilize nature, we find that the better that's going to be.
Great. I don't know if let's move on to outer space, and then we'll circle back to the biohab questions. So
okay. All right, so hopefully you're seeing space architecture now. So, now we're going to go a little bit off planet. This is our project with NASA. It's through the NIAC program, which stands for NASA Innovative Advanced Concepts. The primary investigator on this is Dr. Lynn Rothschild at NASA Ames. And we met at a biomimicry conference where, I was talking about this concept of, one day we hope we can create food and materials from the bush in Africa. And she's like, well, I like that idea. Do you think you can do that on Mars? And my first question was, well, I don't think there's any bush on Mars, right? So what are we going to use as the biomass? What is the waste resource that we can use? And it didn't take us long to figure out, she happens to be an expert in cyanobacteria and different blue-green algae, and was developing technology already that was going to leverage the fast growth of those microorganisms to create materials. And so, we thought, okay, two-step process here. We're going to go off planet. We'll grow these, autotrophic organisms that are going to leverage light and water. And, at that point, Obama was president, and we were going directly to Mars. So we knew there was going to be carbon dioxide when we got there. So we can use CO2 and water and light to create these, algae. And then the algae could be the substrate for growing our, mycelium composite. So that would be our biomass that we created when we get there. So it's, it's a pretty simple idea, really. You just go and you create a bioreactor that will work in that environment, and basically just add water. So, it seems simple, but we got through the phase 1 with a proof of concept that kind of said, yeah, we can, 1 + 1 = 2, and we think we could do that. And now we're, in our phase 2 of this project, we're starting to prototype these things. It gets pretty complex, but as far as the complexity of most building materials, if you think how vinyl siding came to pass, all the way from dinosaurs to the lab that kind of turned these polymers into actual materials, we feel like that this is actually pretty simple when you come down to it. You're basically going to grow something in a sealed container, and it's going to fill the cavities of an inflatable object. So the main question is why do it this way? And the way that we pitched this to NASA, firstly, was that you would be able to turn a very small amount of material that leaves the gravitational well of the Earth into potentially millions of tons of material at destination just by adding what they call in situ resources. If you look at the numbers here, basically, some projections show that it could cost as much as $1 million to get 1 pound of material to Mars. It's actually close to about $1 million to get a pound of material to the moon now on some of the lunar payload services contracts. So, but if we were looking at lots of missions going to these places, they think they can get that down to as little as $100,000 to get 1 pound. So a can of soda basically will cost you $100,000. Obviously, you don't want to take a lot of concrete or bricks or lumber to do that, and as little metal as possible to do that. So what we propose is basically a material that can be grown in situ to create, again, potentially millions of tons of material, which could save trillions of dollars. And so that sounded good to NASA, and that's why we're kind of rounding phase 2 into phase 3, where hopefully we'll be sending a model of our project to the moon in phase 3, which could get there as soon as 2025 to have a really very, very small scale demonstration of this. And again, it would probably cost $1 million to get this scale model there, that being something that weighs around a kilogram to get there. But yeah, here's the process in a nutshell. And it's if you look to the left, you'll see a a scale, basically showing the weight of the material, the mass of material. If we were to take a 10-ton object, which obviously would be very heavy and very expensive, that could grow into something 10 times as big, you're basically saving or it's costing you 10% of the cost to get a large structure there. And you see as it's filling up with water, the bioreactors are now starting to fill with water, which enables these autotrophic organisms to grow with artificial light that would be kind of up against these reactors. We create these filamentous colonies of the blue-green algae that then becomes the substrate for growing mycelium on, creating these composite materials that are insulative and radiation attenuating. And those are the two main reasons, but it's also protecting from things like micrometeorites, and it's giving you a solid structure where normally this would be an inflated structure, which has all of the disadvantages of living inside of a balloon, really. Here's a section showing how artfully we can arrange some of the reactors of this to create kind of an experiential thing. This was one of our concepts where we were just kind of going for glam and glitz. The one that you saw that was in the animation, I think is the one that we're developing further. It's going to be very rational, and it's going to have these bioreactors that are kind of linked up in series and easy to grow, comparatively to something like this. But this just shows that there is opportunities for actually having these bioreactors be an experiential part of the architecture as well. And this kind of paid homage to another project out of NASA Ames that was called Water Walls, where they basically were using these algal reactors to process human waste into converting it into oxygen and biomass that could be used for beneficial things, but also with these bioreactors, these water walls that were part of the exterior of the building, the water becomes a radiation attenuating material in itself. So there's a lot of things that could be leveraged here, and circular economy is kind of the name of the game for folks at NASA. They famously describe the coffee on the International Space Station. They say that yesterday's coffee is tomorrow's coffee, because they recycle their urine basically into the water that creates the coffee going forward. So there's a lot of circularity that needs to happen there, because there are very little resources that you can use once you get to destination, and obviously you don't want to be polluting as well once you get to a new destination. We want to maybe this time build the right way. So we kind of look at this as the inverse of what we've done on Earth with architecture, where architecture and development can be seen as a great destroyer of nature, whereas this is something that actually is the seed of life when it gets to destination. And I kind of like to think of the Neil Young song about after the gold rush, flying Mother Nature's silver seed into a new home in the sky, and actually having Mother Nature fertilize a new planet by having some of these biomaterials be the architecture. But anyway, so to compare this to different in situ resource ISRU materials, which stands for in situ resource utilization materials, we fare pretty well on all of the metrics. When it comes to things like compression and the R value of the material, the temperature to produce, all of those, they fare pretty well. And the modulus of elasticity is actually, something that we're going to look to a little bit more than the compressive strength when it comes to these materials, because gravity is less there. That's not the main point that keeps us from looking at compressive strength as the main thing. It's actually that the architecture that we'll be living in, or the explorers will be living in, are going to be pressurized vessels. So all of this material is actually going to be pushing outwards. So the mycomaterials, in conjunction with the inflatable fabrics, do form a very good composite that's great for tensile strength in this regard. So again, those materials kind of working together, but the inflatable product, in this case, it's going to be Vectran coated meshes that are polyurethane coated Vectran material. And Vectran's a little bit like Kevlar, but it's good for UV protection as well. So there'll be these really high-tech materials that are kind of working in concert with these you could call them low-tech materials. They're basically these grown materials that can do the other things. So what are we looking at here? We're looking at mechanical properties, but the two main things that we need to look at with materials off planet are going to be the thermal insulation and the radiation protection. So once we get outside of the Earth's magnetic field, we're exposed to lots of ionizing radiations, things like X-rays and gamma rays, and also particle radiation is something that we need to kind of look at. And so materials that have a lot of hydrogen bonds to them end up being really good at particle radiation, and things that have high electron density are good at things like the electromagnetic radiation. And fungi are particularly good at some of these things because of a concept noted as radiotropism or radiosynthesis. And that's the ability of several fungal species to harvest usable energy from forms of ionizing radiation, such as gamma radiation. The image that we're looking at there is the reactor at Chernobyl, and this phenomena was noticed in near Chernobyl when there was a proliferation of dark fungi that was growing near the reactor, actually in the reactor, and throughout the basically this whole area. A lot of researchers brought those into laboratories and started testing this, and found out that the organisms do grow towards the radiation source, and in some cases they actually use the radiation source as a nutrient, very similar to how plants use radiation in photosynthesis. These fungi are able to use this high energy radiation to convert it into benign forms of energy. So we're working with some of the researchers that did these initial papers and have been writing about this ever since. Folks at Johns Hopkins, including Arturo Casadevall and his protege Rodimus Cordero, who are writing a lot of papers and doing a lot of studies on this concept of radiosynthesis and radiotropism. And they're looking at it, from a medical standpoint, but also Rodimus is specifically looking at it as a material that could be used off planet to protect from ionizing radiation sources. So with the folks at Johns Hopkins and with folks at NASA Glenn and University of Akron, we produced a few different samples that used this melanin-rich fungi. We made some samples that were mycocomposites like we normally make, and then were some samples that were made of pure melanin that was extracted from fungal organisms, and some that were produced synthetically. And the reason we looked at melanin specifically is it seems like that is the biochemical that is creating that transduction of energy. And so melanin is something we have in our skin as a pigment that protects us from UV radiation. Actually, all five kingdoms happen to utilize melanin in different ways, but usually as a UV protectorant. So we made these samples and we put them into these aluminum containers, and then those aluminum containers went to the International Space Station. So you see here with a couple of astronauts, and then they put them outside the space station. So you can see the materials there on the right, the circular materials and square materials are basically exposed to the vacuum of space at this point. They have 4 different directions that they face, either towards the sun, away from the sun, towards the earth, and then out towards basically out towards space. And they basically test these materials in different locations to see how they fare with space radiation in low Earth orbit, as well as things like being exposed to atomic oxygen. And here are the samples once they came back. So we had them up there for about a year. They were exposed to the the environment, I guess you could call it, or or lack of environment for 6 months of that year. You know, at several points they had the aluminum panels covered when there was traffic going in and out. Seems weird to say that there was traffic at the space station, but there's usually a lot going on up there that, you know, we don't know about. And apparently throughout this the entire year that they were there was only about 6 months of that year that they were able to expose these materials. So you can see that there is, you know, on the flight one, there is some degradation to the material, but it's actually very little compared to a lot of the materials. Some materials don't even come back. They just get totally baked and disintegrated and turn into dust and are basically still flying around up there somewhere. And it's problematic because there's a lot of what they call van der Waals forces that basically makes the dust from those things stick to other things, and it's you know, kind of hard to clean the space station, so it's that's a problem. So they do a lot of testing before they allow materials to go up there, and, you know, shake resistance and some of this you know, degradation testing, but nothing really compares to actually being outside the space station in low Earth orbit for 6 months. And what we did, we're doing loads and loads of tests now, and I say we, I actually mean the scientists. So folks at NASA and Johns Hopkins are doing loads and University of Akron are doing loads of tests on this. This was one that, you know, we did right away as soon as it came back. Basically just looked at these materials that we put behind each one of these as dosimeters, basically to compare the flight and the control, and to see, you know, how much radiation actually penetrated these materials. And, you know, just the initial studies show that, you know, all of these are very effective at blocking from radiation. But the one that was, you know, fared the best was the pure melanin that was extracted from fungal mycelium. And since this is a you know, myco group, you're going to ask what the species was. It's Cryptococcus neoforms. It's basically a yeast that can produce loads of melanin, and that's what our, you know, friends at Johns Hopkins are mostly using to grow, cultivate, and extract melanin from the mycelium. The folks at University of Akron actually made synthetic mycelium. There's the way, you know, way I don't understand so much, but from the L-DOPA, basically chemical, you can create synthetic melanin, and basically that fared fairly similarly. And then our mycelium composite that we made, that was just basically the materials that we make this, like we're doing in Africa, like we're doing in Cleveland. They you know, fared similarly, but with a wider range of protection. So, you know, some good parts and some not so good parts, but all of these fared better than pure PLA, and way better than the control. You can see in that very far left corner, that's what happens to PVC when it's not protected. It basically, you know, turns into a brown material from what was clear. So that was our, you know, very simple dosimeters, but we're in the process of actually doing, you know, micro CT scans and all kinds of things. Some of the folks at NASA Glenn have already found micrometeorites that are lodged in the material. So yeah, didn't make it through, but those are basically small particles of exploding stars that are caught in the materials. And that's kind of cool to think about, that, you know, that this fungal mycelium was a catcher's mitt for an exploding star. I will just end with this other animation that I have here, and this one's a little bit more, you know, sci-fi. It's a little bit more magical. You know, the idea of this rover actually inflating the you know, this very artistic version of our mycotecture off planet. But you know, the reason we created this is we wanted to show that it's not just a building that we could create using these methods. If we can create these inflatable things that could fill with growing materials that then become solid materials at the end of the day, with different densities, basically from the compaction that would be based on the air pressure that we could build, you could get everything from a very soft couch to a, you know, a strong end table, and even, you know, a piece of equipment like some of the exercise equipment you see there, and, you know, furniture like countertops and beds, and, you know, you name it, there's probably a fungal species for every every piece of furniture. And you guys are very familiar with, you know, Myco works and their products, Ecovative and their products. So there's different densities, different you know, softnesses, and either leathery type materials that can be created using, you know, the or similar biomaterial, biofabrication or biomanufacturing. So you know, this is kind of aspirational, obviously, but, you know, we could imagine a future where every bit of our architecture is actually grown, and potentially grown in situ. So I'm gonna stop it there, and I hope you have questions for me, and I'm happy to stick around as late as you all are.
Actually, can we ask you to turn your video? Oh, good.
Yeah,
Great.
sure.
Great. And I think my brother was making a joke because that little brown smear with the PLA, he was talking about the Maillard reaction. You know, that it just basically caramelized and there wasn't anything left.
Yeah, so that's the PVC. Basically, we had those as dosimeters behind all of our samples, and you know, one that didn't have any protection to it basically turned into the, you know, that brown mess. And that was, you know,
Right.
just from the space radiation and from you know, atomic oxygen. So here we, you know, on planet Earth, we have diatomic oxygen. It's O2. That's what we breathe. It's fairly reactive, as we all know, but you know, atomic oxygen, you know, singular oxygen atoms are extremely reactive, and that actually destroys a lot of materials in low Earth orbit as well.
Interesting. So I wanted to just go back and make sure we caught some of the questions at the end of the Biohab Namibia project. And then I think we'll just let people unmute and ask questions after that. So there was somebody who was concerned about whether the encroacher bush would be allowed to grow back. Like my understanding is that it's sucking up the water table, and so they don't want it to grow back.
Well, so the government of Namibia wants to thin it to a, you know, a reasonable percentage. So there is a what they call an transpiration tree target, basically. You know, so it's a certain amount of that biomass that they want per acre. And so the goal would be to not eradicate all of the bush, but would be to thin it to that level that creates what they call a bushveld, or, you know, the combination between grasslands and bush that is more in line with what nature intended for that area. And there is about 300 million tons of biomass that should be, not could be, but, you know, they want to be sustainably harvested every 15 years. So you know, we basically figured out if we could have 1% of that, we could house all of the 500,000 people that are experiencing homelessness in Namibia right now. We could create, you know, hundreds of hundreds of tons of mushrooms yearly. So, you know, enough to flood the market with reishi, you know, worldwide. You know, just taking a fraction of what biomass is available for that. And that biomass is being used currently for creating fuel pellets. And, you know, I don't want to disparage that too much, because that's obviously much better than coal and fossil fuels as far as a fuel. But, you know, just, you know, looking at this resource and saying, what can we do with it? We should burn it. Doesn't sound great to me, but, you know, it's definitely better than what's done now, which is coal fired plants. But if we could just imagine a scenario where we're using most of that bush to create food and housing, that could make a real big change, especially since that's drawing down carbon, and then we're putting that into something that's going to store that for for years and years. We're actually looking at a process that could leverage this blight on the landscape, which is this bush, to be something that's positive for the atmosphere.
Right, and then someone else asked about, so, Nakakande Josephine, she's in Uganda. She's doing a lot of humanitarian work around mushrooms. Has anybody connected the two of you? Are you familiar with her kind of efforts in Uganda?
I'm not. We have someone in our organization that recently met with officials in Uganda about a possibility of doing something there. But yeah, we teamed up with folks in Namibia that were already starting to research the ability to take this encroacher bush and turn it into food. We just kind of added this extra step of creating buildings from the waste that comes from that. So it's a circular process a couple times over.
Cool. And then somebody was asking, going back to biohab, can you compress, instead of, I guess, squishing it that way, could you compress it into a 2x4?
Yeah, we could. So we kind of think that the best way to do this would become to make these massive slabs of material. So the reason you have these 2x4s is because you want to use as little wood as possible, but with material that's actually creating using a waste material, there's no guilt behind using loads of it, and actually you benefit by using lots of mass, and so you can create these massive objects out of that. But yeah, again, the materials we make, if we were to make 2x4 type structures, we would have to work with a lamination of that in a way that would enable it to be as flexible as ductile as wood is, and that's another reason we go with these massive slabs of materials, just because you get the brute force of having the mass behind that.
Right.
So the short answer is yes, but we're going a different route because the benefits of this material are different than benefits of other materials.
Right, you don't have the constraints. Yes,
Yeah.
that's great. So I'm encouraging, I would encourage people to go ahead and unmute. I don't know if I missed anybody's question, or if there's some people developed some other questions while watching this. Go ahead and unmute and have your video on, please, and ask your question. You could, if we want to do it in an orderly fashion, there is a reaction thing where you can raise your hand and it'll pop you to the top of my screen, and that makes it easier to find you. So
See EB.
Can
think
anyone
Gail-
hear me?
Yeah.
Oh,
Can you guys hear my voice?
Yes.
Okay. Zoom normally doesn't let me partake in this, so this is amazing. We've been sitting here and my mind is blown. The work you're doing is awesome. I absolutely love it. And the Uganda question was ours.
Okay. Yeah, we'd love to touch base with those folks, especially since we are starting to get into Uganda. There are some officials there that want to bring
Nakakande, she's an amazing person. She's built a couple schools already.
Oh, cool.
We've helped her as much as we can from here, but I would love to link you up with her.
I'd appreciate that. Thank you.
I am going to pop Chris's email address into the chat so that everybody can grab it from there. So, Sam, are you?
Cornelia, would you
Yes.
please give everyone a heads up how they can copy the chat?
Right. And so at the very bottom of the chat, first of all, you want to open the chat, which is down at the very bottom of your screen. And then there is a little group of 3 dots. And then when you click on those 3 dots, it gives you the option to save chat. And we'll, yeah, so it's at the very bottom of the page. Save chat is the first option in the menu that comes up. Okay. Gail, did you have another question? You have to unmute though.
I was just looking for his email address.
Okay, I'm trying to do that while I'm checking to see who else wants to ask a question. I thought Mark was going to ask a question too.
Yeah, if anyone's got issues with getting to the chat, it's Chris at redhousestudio.net. So CHRAS at redhousestudio, make sure that's singular, .net.
Athena just put it in there.
Cool.
Great, thank you.
And Chris,
Yes.
I was wondering, did you grow up with parents who did social activism or volunteering? I mean, how did that spirit get imbued in you?
A little bit, yeah. So my folks definitely encouraged that. We did a lot of work with we happen to have migrant workers that come through my area of Northeast Ohio, and we had a basically an outreach. Our neighbor had started an outreach program, and basically we volunteered there quite a bit, and stuff around church oriented stuff probably. So yeah, I think I could say I got that from them. I think my experience in Africa was really transformative to kind of turn that into something that was maybe thrust upon me as a youngster into something that I felt passionate about, because it enabled me to use my love of architecture in a way that was kind of humanitarian based as well. So when it was volunteerism as a youngster, again, that was maybe something that was kind of more like a chore. But when it came to being able to use creative ability to get into the realm of social impact, that is something that I wouldn't give up even if somebody tried to force it upon me.
So Gail is saying you should be nominated for a MacArthur Award, which I
Boy.
agree.
I think they're announcing them soon. I saw that email. I was like, no, I probably won't get it.
Well, at least you get our vote. I know that we're not voting.
Okay.
But
Yeah.
I also thought it made sense to actually share about the Bioscene conference
Yeah.
where you hooked up with MIT and
Yep.
NASA. And so I have the link in the chat I just put, but I thought it would be great to hear you say a little bit about it.
Absolutely. Yeah. So that's another thing that I found a lot of the collaborators that I'm working with now at this conference. It's called Bioscene. It's part of NASA. So NASA Glenn is based in Cleveland, Ohio, where I am. And they have a biomimicry group based out of there that's called VINE. Everything's an acronym with NASA. So VINE is the Virtual Interchange for Nature-Inspired Exploration. And they started this conference that started as with different names, but has evolved into the Bioscene. And between NASA, Glenn, Great Lakes Biomimicry, and the Ohio Aerospace Institute, they host this conference every year on biomimicry, and it's not always based in aerospace, but there are certainly lots of folks interested in that, being from NASA. But it's about biomimicry and engineering mostly, but also in art and design. And so I'm curating the art and design component to this year's conference, but there'll be speakers there that are from industry, from academia, from NASA, and there'll be this year's theme is materials, so I plan to be kind of involved with that one. And every year it's a different topic, but it's always based around biomimicry. And so I think you guys probably know what biomimicry is, but an easy definition for that is looking to nature for inspiration on everyday issues, usually in engineering or something like that, where we're going to have a problem and we're going to say, how does nature solve this problem? And then, by doing that, you're basically mining, 3 billion years of innovation. And, kind of cutting to the answer, that took nature maybe 3 billion years to figure out. But nature found a great solution for what you're looking at, probably the problem you're looking at most likely. And so, easy examples of that are aerodynamics when it comes to aerospace and things like that, or bullet trains, and different looking at aqueous animals for things like fluid dynamics, and but also things like how does bioluminescence work, and how does circulatory systems work when it comes to heat exchange and things like that. So a lot to be mined there, but this is at it's outside of NASA Glenn's campus at the Ohio Aerospace Institute. It's October 18th through the 20th. I think registration might still be open. They might have closed it, but if you send me an email and say you really want to go to this thing, I'll do my best to get you in. But there is a virtual, no, I'm sorry, there isn't a virtual component this year. It's all in person. So, if you did want to do this, you'd have to come to the Cleveland area, which, it's not a punishment. You can have a good time there. Sam and Cornelia will tell you it's not so bad. But yeah, just a really fantastic conference, and really smart and innovative people there. And I met a lot of my collaborators, including NASA and MIT, by going to this conference.
And we do still have some materials type questions, actually, that
Okay.
apparently people are wanting me to ask because they're not raising their hand. But so the laminated sheet materials, is there a practical size limit? And what's the density, like weight per meters cubed?
Yeah, so it'd be similar density to the other materials we're making, which is about 0.6 grams per cubic centimeter. So similar to woody materials. The limitation on size would probably have most to do with transportation. So if it fits on a flatbed, that's a good unit of measure usually. So you're talking like 8 feet by 40 feet or something along those lines, and you can get pretty big slabs of material that way and actually erect buildings very quickly. Here in Cleveland, we actually have the nation's largest cross-laminated timber building, and it's 9 stories. That's a high rise, but the instead of using concrete, pouring concrete into these big things or erecting it with steel, they use these huge slabs of wood. They're about 8 inches to a foot thick, and then they just lift them into place, and then they could go floor by floor by floor. They did like 9 stories in a week or so. I don't know. It's probably a little longer than that, but it seemed like it went up almost immediately just because they could lift these relatively light materials into place, and the floors are fully done just by setting them in and tying them into the columns.
I hope somebody did a time lapse of that. That sounds amazing.
I think so. Yeah, the project's called Intro. So I'm sure it's they had some really savvy developers. So Intro Cleveland.
Okay.
If you look into that, I'm sure there's stuff on their website or maybe YouTube of the construction of that. But yeah, it's again, I really like the technology and the fact that it's lightweight and easy to erect and stores carbon, but there is the problem of using virgin lumber, and if it proliferates the way that the market projects, it's going to cause some real problems real soon. So that's why we want to get into that market right now, and and kind of show this material does the same thing as that, but it utilizes waste resources instead of forests.
So I think Catherine's question is related to that. What is there value in cross lamination of the composite mycelial material,
Mhm.
given that you don't have any directional fibers like you do in wood?
Right.
So
Yes, lamination, actually, that's one of the strongest things in plywood is the glue.
Right.
Yeah, and woodworking, the glue is actually, a lot stronger. But not only that, but it's having those veneers, having different material changes through there. So
Right.
that's good for mechanical properties. It's good for thermal insulation to go from one material to another, to another, to another, to another. And so, you have the any heat that's trying to transfer that has to kind of change speeds. So it's good for thermal transmission as well. But yeah, certainly structural or, mechanical properties are heightened by using just that lamination method.
Cool. And then Mark was asking if you've worked with industrial hemp and mycelium to make any building blocks. And actually, Mark, I'm curious, when you're saying industrial hemp, what do you mean? And I think you'd have to unmute to answer that, but or you want to type it?
Well, I will say yes.
I-
We used. Oh, go ahead. Sorry.
Yes, industrial hemp is just the type of hemp crop that they make my blue jeans from, all sorts of hemp clothing,
Mhm.
sails, rope.
Mhm.
It's been
Yeah.
used for hundreds, if not thousands of years.
Okay.
It-
There's just a lot of also hemp from the cannabis industry.
Yeah.
So I'm curious, when you said industry, so
it-
thanks for clarifying
industrial
that.
as opposed to medicinal or
Yeah.
Great.
Yeah, and so with either one, with the hemp plants, there's different parts to that can be utilized for different things. Obviously, if we're talking marijuana, the flowers are good for lots of things. But when it comes to hemp, which I think you're referring to, that doesn't have any of the or less of the cannabinoids and less of the THC. The fibers of that are what's good for making jeans out of. Ropes and different textiles out of. The byproduct from that is called hemp hurd, and that's just kind of like cellulosic waste that is the byproduct of harvesting those fibers. That's what a lot of cultivators can use to make to do the process we're talking about here. So you could make building materials. You could make grow mushrooms on it. I think Ecovative actually uses hemp hurd in their mixture. And we have used it before, but mostly in a product that's called hempcrete, or people have different names for it, but basically you take that hemp hurd and you mix it with lime, and then that becomes a massively insulative product. It's not really structural. You have to use it in conjunction with wood bearing construction, like 2x4s or 2x6s ideally, but it has that carbon storing ability of just using that waste resource for something. The reason we don't use that in our biocycling or our material production is it's really expensive still, even though it's a waste product from the industry. It's packaged and sold at pretty high rates, and I would love to do more hempcrete type construction, but it's cost prohibitive in this part of the world. And even we have a project in Colorado now. I thought for sure it'd be cheaper there, but we can't get a good source of the hemp hurd for doing that there. I think it's the processing involved, and then certifying that as a product that can go out for other industrial uses, but for whatever reason we can't get that affordably. The sawdust that we use for our work in Cleveland is stuff that we sweep off the floor in a sawmill near us, and the stuff we use in Namibia is the waste from the encroacher bush. So it's extremely cheap substrates and materials that are easy to gather. We look to a future where hemp could be more accessible, but right now it's too expensive.
Thank you.
Thanks.
So someone was reminding me that one of our huge agricultural waste streams in Georgia are all the peanut shells.
Mm.
which actually, I know that someone at Kennesaw was trying to look at growing patty straw mushroom on, but
Uh-huh.
this actually is more interesting in a certain way, like making building block materials out of it,
Yeah.
even if you didn't get a culinary mushroom out of it.
Yeah. Yeah, so
Yeah.
that's a good example. What we would do at MycoHab is, if we were going to do something in Georgia, we would look at all the industrial and the agricultural byproducts there, and we try and identify the one that, would be the most valuable resource in the fact that it's the least valuable resource, right? So it's, something that's going to waste or possibly causing detriment, and then convert that into something positive. So for instance, if that is what you identified in that part of the world is something that we could use for that, we would test that right away, and we would kind of find out what the biological efficiency of using that as a substrate is, and then the mechanical properties of the byproduct material that came out of that. And we run those tests on all of the different options, and kind of maybe come up with one or two materials that makes a cocktail that would work well in that region. So I'm sure a lot of folks in your group have looked in that too, like how can we use these peanut shells in certain ways. So yeah, it's really interesting to think about that, and it seems like it would be a great substrate, right?
Does.
Yeah.
I remember Phil Ross telling me that apparently pistachio processing waste, like Reishi totally adores that stuff.
Oh yeah, yeah,
It's interesting. I mean, I don't know who else you would hear that from, but because
yeah.
he's out of California, he knows
Right.
about
Yeah, so California, one of the things we would look at there is probably almond shells as well. There's a
Right.
lot of nut farming there, and we hear from farmers that this is a waste resource we have, and they would love to sell it. So usually when you have something that you're paying to give away, you would love to find a use for it, right?
Right.
Yeah.
Great. Well, thank you. A lot of people are putting their thank yous in the chat as well.
Mhm.
So, this was amazing.
Well, thank you.
Love
It's been
this.
fun.
Yeah. Sam, anything you want to say in closing here?
People look for this on our YouTube channel in the next, probably take about 4 or 5 days for it to get processed and edited and everything. But then feel free to check out other speakers, and consider, if you're not a member of the club yet, consider supporting the club so that we can keep bringing great speakers like this and continue to do good work. And also support your local club if you're not close.
Yes. Great. Thank you. Thank you so much again. That was so much fun and so interesting.
Thank you all.
I just want to thank you all for the invite, and I really want to thank you, Chris, for sharing this. You've got my mind going. Thank
All
you
right.
all so much for having us and inviting us.
Yeah. Nice. Well, thank
You're
you.
welcome, Joe and Brenda, and we'll keep you in the loop.
Look forward to talking to you soon, Sam.
Yes.
Gabe, we need to talk some more at some point. So
Yes, definitely. Let me know.
okay. All right.
And Sydney, we'll be out of town next week because we're teaching our class at the John C. Campbell School. Hey, Alan.
Great presentation.
Thank you. But Sydney, I'll give you a call in about a week and a half after we get back.
All right. Great.
Thank you, Sam.
You're welcome. Look forward to seeing you, and look forward to seeing all of you whenever we can. And it's great that we've got at least 3 people from the Mexico trip, and we've got a couple of our upcoming students. So yay. So you can look forward to this kind of fun in class.
All right.
All right.